Well, we continue exploring graphs of various functions. One of the most interesting functions, or the funnest functions to play with, in my opinion, is these kinds of things. They're called rational functions. I'm going to show you an efficient way to graph rational functions. And part of the thing with rational functions, when you have some polynomial on top, some polynomial on the bottom, is you often get asymptotes. And so we're going to see a couple asymptotes show up like right now. Ready? Okay, so we're going to graph this the way we usually do, the shotgun approach that we've been taking for now. And remember when we were talking about centering your shotgun, you look for values of x that are interesting. Like here, isn't x equals -2 rather interesting? Because that'll make a zero denominator. And you know that a zero denominator is undefined. You can write undefined here, or you can have a little more fun. I like to write boom. Boom! It blows up! It literally blows up. You explode the function. You cannot take a -2 without it going like to infinity, because you're dividing by 0. That's as you divide by something closer and closer to 0, you're blowing up towards infinity. So it's a boom. It's a big boom. So I'm going to put a dashed line along -2, and it turns out this really is a vertical asymptote, and I'll prove that to you in a little while. But for now, let's just put that dashed line there to say, you know what, when you have x equals -2, there is no y coordinate. There is no point anywhere along that line. No point. And let's then march a little bit to the right, plug in x equals -1. What do you get? You get 1 over -1 plus 2. That's a 1 over 1. That's a 1. So when x is -1, y is 1. Boom. Let's plug in a 0. So when you plug in a 0, just look at this thing here. 1 over 0 plus 2 is a half, basically. So when x is nothing, y is a half. Let's plug in a positive 1. Now you've got a 1 over a 1 plus 2 is a 1/3. Let's plug in a positive 2. You get 1 over 2 plus 2, that's a 1/4. And you start to see something here. If you plug in a 3, now you've got a 1/5. If you plug in a 4, now you've got a 1/6, and so on and so on and so on. As you go closer and closer to infinity, and it's a little improper of me to write like I'm plugging in x equals infinity, but just think in terms of plugging in x equals infinity. What would happen here? You'd have 1 over, and just to be weird, you'd have infinity plus 2. Now, adding 2 to infinity is a completely meaningless concept. You cannot add anything to infinity, right? Because infinity it's not even a number. It's a process. It says keep going. What are you supposed to do? Keep going and then go 2 more? No, you just keep going. That's enough. Keep going. Anyway, 1 over infinity, I'm using an arrow because I'm not saying equals. It's definitely not equals, but it approaches. It gets closer to. And 1 divided by a really big number, if you try that on your calculator, 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000, you getting 0.000, right? It goes towards 0. So that's what we mean by a horizontal asymptote. Horizontal asymptote, which is spelled up here, asymptote. For some reason I could never get my spell checker to accept the P in asymptote, but I know it's there. I know it's there. So anyway, as x goes to infinity, y is going to 0. It doesn't equal 0, but it's getting there. And so the way you show that it's getting there without actually reaching it is you draw an asymptote here. So notice what we have here is we have what's called a horizontal asymptote. And it's nice to specify the location. It's along, well, all of those points have a y coordinate of 0. Y equals 0 is you could consider y equals 0, this little mini equation is the equation of this line. It's the equation of the x-axis. So horizontal asymptote along y equals 0. So if you want, you can carefully plot these points, but I don't have to be that careful, do I? We know what it's doing. It's going towards, without ever touching, it's going towards the horizontal asymptote. That's a horizontal asymptote. Let's see. Do I have a formal definition here? Well, I don't think we have to write anything down. We get the idea, don't we? Okay, now let's look at this boom thing here. Let's take a closer look at this boom thing. So in other words, I'm going to start a new xy table, and I'm going to, well, I had already used x equals 1, So now I'm going to use like maybe or I should say -1. Now I'm going to use -1.5, and what I'm going to do actually is I'm going to get out my calculator. I'm going to plug in values that sort of get closer and closer to the -2 without hitting it, and I did. So at -1.5, I plugged into, and I plugged into this formula up here. If you plug a -1.5 in there, well, you could do it right now. -1.5 plus 2 is a half, and 1 divided by a half is indeed 2. But I plugged in -1.7, and I got basically 3 and, did I really get 3 1/3? I guess I must have. Okay, because I wouldn't have written it otherwise. So I got 3 1/3, and then when I plugged in -1.95, I got, ready? 20. Okay, it's getting bigger. And then I said, hey, you know what? I'm going to plug in -1.995. And all of a sudden I was at 200. Okay, and as you know, when you get to -2, it's Boomsville. So you start to plot these points. -1.5, x is -1.5, I'm at y is 2. X is -1.7, I'm already at 3 1/3. Not there, 3 1/3. 3 1/3 or something, somewhere like around here-ish. And then -1.95, I was already at 20, so I'm off the graph already. So you can kind of see, yeah, it's blowing up to infinity. And why is it blowing up? Because as you get closer to -2, whoops, that's not an eraser. As you get closer to -2, this is getting closer and closer to 0, right? So if x is -1.95, I got a -1.95 plus 2 is a 0.05. If x is a -1.995, then I've got -1.995 plus 2 is a 0.005, and so on. So as x gets closer and closer to -2, you're dividing by a smaller and smaller number, which gets you a bigger and bigger y result, and hence my little phrase or whatever, blows up to infinity, is actually, you couldn't say that was inaccurate, could you? It's blowing up to infinity, boom, as x approaches -2, and it's important to say from the right side. As x approaches -2, you can tell by looking at the formula, this is blowing up towards infinity. And that's the nature of a vertical asymptote. So keep in mind, I think I'll do this cut stuff. Keep in mind where vertical asymptotes come from. Vertical asymptotes come from a division by 0 error. In fact, I'm going to write that down because that is worth writing down. As soon as I get my pen to work. What is the problem here? Come on. How am I not used to this thing yet? Okay, well actually, you know what? I have only one eye today because I just got my cataract. So I got this big thing and my glasses don't even fit, and so I'm allowed to make mistakes today, right? Right. Anyway, vertical asymptotes occur where there is a division by 0. And when I say where, we're always talking about x coordinates when we say where, right? Y coordinates are what? It's like, what is it? It's 5. Really? Where? Where tells you the x coordinate. Anyway, I don't know any exceptions to this, so I'm going to say it's a law of life. Vertical asymptotes occur where there is a division by 0. So when you're playing with rational functions, you can right away say, hey man, there's got to be a vertical asymptote along x equals -2. Because I'll have a division by 0. Now that's not a completely accurate statement, but you'll see that come up in the example later. But it's a good rule of thumb. Now we shouldn't say we're done with this example, right? I've had a lot of people do that. They get the horizontal asymptote, they get the vertical asymptote. By the way, let's be complete about this, and let's say we have a vertical asymptote along, what would you say? Well, all of these points here have an x coordinate of -2, so a good idea is to say along x equals -2. So it's like, you know, this mini equation here, x equals -2, it actually represents this vertical line, because that's where x equals -2, all up and down that vertical line. So this is how you write the equation of a vertical line, by the way. Okay, so let's see, let's get rid of some of this green stuff. Okay, but anyway, what I was saying is we're not done. I mean, there's got to be something going on over here, right? So you should be plugging in more values here. Boink, 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 boink. Okay, plug in some more values. So maybe I'll just start making up an XY table over here. Now you know that -2 is going to be a boomer. And let's kind of go further to the left. If you plug in a -3, what have you got? Well, our function is, remember, 1 over x plus 2. So if you plug a -3 in there, you'll have a -1 on the bottom. 1 over -1 is a -1. If I plug in a -4, I'd have a -4 plus 2 is a -2. 1 over -2 is a -1/2. Okay, so when x is -3, y is -1. Oh, it's down here. When x is -4, y is -1/2. Okay. When x is, you can kind of tell what's going to happen here. It's going to be like a mirror reflection. So it's we've seen these kinds of graphs before, right? The old 1 over x type graphs. There we go. So we're kind of like doing the splits around this point here. So we've got this part over here, and then we've got this part sort of rotated, if you will, over there. Okay, I think that's a good, I think we can stop with the function there. So now you know what these vertical asymptotes are and where they come from. They come from division by 0. You know what a horizontal asymptote is. And by the way, how do you detect a horizontal asymptote? All you really do is you think in terms of, well, if I plugged in something really big, what would I get? I would get basically 0. That's how you know. And I suppose you could plug in -infinity. So you go to 1 over -infinity, but that's still 0. It's like -0. Although, you know, that's kind of meaningful because, look, when x was going towards positive infinity, we were going towards 0 on top. And when x was going towards negative infinity, we were going towards 0 negative values, so from the bottom, basically. So that's pretty cool, right? So you can tell stuff. You can tell stuff. Okay, so, like I say, now that we... quick, this is just an aside. This is just an aside. Oblique asymptotes. First of all, what are they? They're asymptotes that are not vertical, they're not horizontal, they're like straight lines that go at an angle. So these occur, put it over here, when degree of numerator, do you remember what degree means? Degree of a polynomial? It's the highest exponent on x. When the degree of a numerator is 1 more than the degree of the denominator. So if you ever have a situation where you're very interested in asymptotic behavior, if you ever notice that the degree of the numerator is exactly 1 more than the degree of the denominator, so maybe you have an x cubed on top plus 1 or something, and then you have an x squared minus 1 or something, this is going to have an oblique asymptote. This one will, because the 3 is exactly 1 more than the 2. This will have an oblique asymptote. But we're not gonna do those in this course because they require you to do polynomial long division, and I'm not gonna do that. Let's not do that. Just keep in mind that you can actually have oblique asymptotes. So in your future, if you're playing around with asymptotes, just kind of keep that in mind. But let's focus on verticals and horizontals for now. Actually, where are we going with all this? We're actually going to put this to use now. We're going to start graphing. Now that's a rational function, eh? We're going to start graphing some rational functions like we're hungry for them, okay? A nice rational function we can chew on right there. But I'm going to show you a nice... this is going to be easier to graph than you can possibly imagine, okay? The hint is, do not just simply blindly plug in an XY table, because that'll drive you crazy, okay? So you don't do it that way. What you do is you sort of follow my 5-step plan. So my 5-step plan is, step 1. Let me make sure I do the steps in the same order that you're going to do them on the homework. Okay. Step 1. Solve for the y-intercept. That's a useful point to know, right? Where it is across the y-axis. How do you do that? You set you set x equal to 0. You plug in x equals 0. What will we have? We'll have a 2 times a 0 times a -3. So, I'm just putting zeros here. Over a -2 times a 1. And actually, the fact that this is a 0 right here, the whole thing's going to be 0, right? So y-intercept at 0. It's going through the origin. Boom, we got a point. Step 2, solve for any x-intercepts. I'm not guaranteeing that you have x-intercepts, but you can solve for them. How do you do that? You don't plug in 0. You set the function equal to 0. That's kind of like saying set y equal to 0 in a sense, right? Because an x-intercept is going to have a y-coordinate of 0. Set the function equal to 0. Now the nice thing is that this function, it may look hideous, but f equals 0, it's a fraction, right? Who cares what the denominator is? You're looking at the numerator. When the top equals 0, the whole thing is equal to 0, right? Because fractions, 0 over anything is 0, right? 0 over who cares what's on the bottom? It doesn't matter. You just have to look at the top. By the way, 0 over 0 is a problem, but we're not worried about that here. So, not at the moment. So, just look at the top equals 0. And it's already in factored form. What could be better? When does this equal 0 is the question. Well, there's two answers. Either x is 0, so we have x-intercepts at 0, or you could put in a 3. We have two x-intercepts at 0 and 3. Of course, we knew x equals 0 was an intercept, but now we know there's another x-intercept right there. X equals 3. Cool. Next, locate any vertical asymptotes. And remember what we were saying on the previous page. By the way, let me get rid of all this stuff. Remember what I was saying on the previous page, that the vertical asymptotes basically show up when you have a 0 denominator. So now we're looking at the bottom. When does this equal 0? And it's already factored. You got to love that. It's already factored for us. Someone's being really nice. When does that equal to 0? And you have two solutions, which means we have two vertical asymptotes. We have vertical asymptotes, maybe I'll write it this way, vertical asymptotes along x equals positive 2 and also x equals negative 1. Those two values of x give you a boom. They give you a 0 denominator, boom. They give you a problem, boom. You get vertical asymptotes. How do you draw a vertical asymptote? Dashed line, right? Vertical dashed line. So we knew where to put them. I suppose I should have circled this too. You know where to put them. X equals 2 is over here. So we have a vertical asymptote there. Now, part of what this means is that you're never going to do something like this, right? The function cannot cross the vertical asymptote. It can't do it. Because remember, you cannot plug in x equals 2 here. It's not possible. Please make sure your graphs don't go across vertical asymptotes. That's not a good thing. Not a good thing. Don't do it. Remember, we expect on a vertical asymptote, we're going to blow up to infinity. So on this side, it's either going to go up or it's going to go down. And on this side, it's either going to go up or it's going to go down. So we got, a few possibilities here. We'll worry about which one is true later. But that's what has to happen at a vertical asymptote. Meanwhile, we have another one at x equals negative 1. Let's make sure we get both of them drawn in there. So we got two of these vertical asymptotes. And again, we're going to expect kind of like spaghetti hanging from a wall or sinking to the wall or whatever. Two vertical asymptotes. Cool. Now, let's get the horizontal asymptotes. How do you do that? And this is the engineer in me. Mathematicians would never, ever say this. No, they won't say this. Plug in x equals infinity. They will scoff at you. They'll probably slap me. If a mathematician ever sees this, he's going to slap me. I know he is. But I'm going to plug in x equals infinity because I think you know what I mean. So f of infinity, so to speak. Again, very bad form. But 2 times infinity minus 3. Right? All over. We got infinity minus 2, infinity plus 1. Okay, what is this really? Well, we got a 2 times an infinity. Now, the thing is, remember what I was saying before? Infinity is so large that you really can't add or subtract anything finite from it. Take the national debt and pay down $3. Did it make any effect? It had no effect. None. None. And that's not even infinite. It's only 30 trillion or so. That's nothing. That's nothing. That's a drop in the bucket compared to infinity. So what I'm saying is the minus 3 don't matter. And then on the bottom, infinity minus $2. It's just infinity. And then over here, infinity, add $1. Yeah, that's why we keep spending, isn't it? Oh, $1 more is not going to matter. Anyway, so you can see what we got here. We basically got 2, infinity, infinity, over infinity. Now, just like you would cancel x's, you can sort of cancel this out. You can cancel this out, you know, and give yourself some 1s. So what do we got here? We got f of infinity, and I won't say equals. I'll say arrow. That would have been better. Arrow. Approaches 2 over 1, which is 2. What does that mean? As x gets massively big, y becomes 2. Y is going to level out at 2. That's a horizontal asymptote. It's when you plug in extremely large, and I do mean extremely large values of x. And we could do this a little more carefully by saying, hey, let me plug in 1,000. Now let me plug in 10,000. Now let me plug in 100,000, and get out your calculator, push all the buttons. You're going to see it approaching 2. Just, I'm pretty sure people are usually, they accept this. They don't usually fight me over this. So I'll keep going it that way, even though, again, it's not mathematic precision here. So let's see. I wonder if I need to erase some of this. Erase some of it. Come on, you. They had to put that button right next to that button, didn't they? Come on, I'm trying to erase you. Okay. So anywho, what did we just say? We just said we had a horizontal asymptote. We drew it. Okay, good. So I was saying there was about 5 steps. There's 4 of them, right? They're kind of easy to remember because y-intercept, x-intercept, vertical asymptote, horizontal asymptote. What's step 5? Step 5 is to start drawing. Start drawing. And that's why I'll bring in this fact up here, this helpful fact. Whenever you're drawing these these rational functions, which means ratio of 2 polynomials, whenever you're graphing these things, you're going to get some kind of a wet noodle graph. It's just the nature of polynomials. Polynomials do smooth, wiggly things like this, and so the graphs are going to be smooth and wiggly and, you know, whatever. So we know we expect that. Now, take a look at this. Take a look at this point for a moment. From here, we know that somehow we're supposed to go up towards that asymptote, right? So that's kind of telling me something right away. It's like, oh, the graph has to do something like that. Now, here's a question. It has to either sink or it has to turn and go up. Which one does it do? Well, what we got to do is we got to find out. How do you find out? You find out by, well, we still have to do a little plug and chug. So I'm going to plug in x equals, what would this be, like 2.5 or something? You plug in x equals 2.5 and you see what you get. So let's see, where's our question up here? 2 times a 2.5 times a 2.5 minus 3 will be a negative 0.5. 2.5 minus 2 is a positive 0.5. 2.5 plus 1 is a 3.5. And so what the heck is all that? I might as well get out the electronics. Why not? So the 0.5s are canceling, but I'm going to have a negative 5 over 3.5, basically. Negative, no. That'd be a negative. You're getting like a negative 1.43. I'll use decimals. They're a lot easier to graph. So something like a negative 1.43. Oh, well, that tells me it goes down. When x is 2.5, y is negative 1.43. It's going down. So let's see if I can just erase the upper green. Oh, cool. It's going down. So I'm going to leave that. Well, let's not leave that green thing there. It looks weird. But now that I have that graph, that point, I can say, well, it definitely comes up along the asymptote this way. How do I know it doesn't turn and go up this way? Because there's only 2 x-intercepts. There's no more x-intercepts. It can't be doing that. Once it's down, it's staying down. It's going down. And then you know it has to come up here, and it's not going to go back down because, again, there's no x-intercepts out here. It can't possibly do that. So there's that part of the graph. Cool. So, I mean, if you wanted to be, you know, a little, you know, perfectionist about it, I suppose you could, like, well, how do you know it doesn't go there? Whatever. You could plug in more x, y points if you want, but I'm just interested in the basic behavior of the graph. The key features are the asymptotes and the intercepts, and then also the idea that it's a wet spaghetti graph. It's just, well, where is it? Where's it going? Where's it going? Now, over here, What's going on over here? Well, I'm not even going to plug in any points because I know what it has to do. Well, I know what it has to do over here. You know what it has to do over here? It has to do something like this. Because it has to go either up or down along this asymptote, right? It has to level out along this one. And it's not going to go down here. Why? There are no x-intercepts out here. It can't go that way. It has to go up. So there, boom, got it, boom, got it, boom. That's cool. That was nice. One more thing to worry about. What's going on between these two asymptotes? Well, we have that y-intercept right here. That's cool. The question is, does it go down on both sides? Does it go up on both sides? Does it go up one way, down the other? We're going to have to plug in a couple of points. By the way, this brings up an important point that I guess I will put in green here. Let's just kind of put it right here. Important. No, let's not put it over there. I don't like it over there. I want it over here. I'm going to put it over here. Important point. And by important, I mean big, giant, huge point. Yes, you can cross a horizontal asymptote near the origin, so to speak. Near the origin in quotes, because what's near? It just means it's you're not going to cross the horizontal asymptote out here, and you're not going to cross the horizontal asymptote out here. It is going to level off without touching the horizontal asymptote out here. But near the origin, so to speak, just in the general vicinity of the origin, yeah, I could cross that asymptote there. I could. It can happen. Remember, you cannot, the reason you cannot at all touch a vertical asymptote is because there's a division by zero there. No way. No way. You can't do it. But there's no division by zero thing that happens with the horizontal asymptote. It's just an observation that as x gets very big, it levels out on one side or on the other. So again, there's nothing that prevents it really from crossing the horizontal asymptote somewhere in the middle. So we have to treat both. You have to treat it as possible. It could happen. It could happen. So, which kind of values do I have to plug in here? Well, it'd be nice to plug in something over here. Let's plug in x equals 1. What do I get? Let's come back up to the function here. If I plug in x equals 1, what am I going to get? I'm going to get 2 times 1 times... I'm going to get 2 times 1, and 1 minus 3 is a negative 2. On the bottom, I'm going to get 1 minus 2 is a negative 1, and 1 plus 1 is a 2. So what's this? This is a negative 4 over a negative 2. That's a positive 2. The sign is the most important part of this here, so I'm just double checking here. What did I put in? A 2, right? No, I put in a 1. Okay, 2 times 1 times negative 2 times negative 1 times 2. Yeah, it's positive. So it's a positive 2. Look at that. It's on. We actually hit the horizontal asymptote. So I guess that proves my important point. Look, we hit it right there. Boom. So I know that it's going to go that way, and I also know it's going to go up from there. Again, why? Because there's no x-intercepts over here. It can't possibly turn around and cross the x-axis because there's nowhere for it to cross. Once you've solved for the x-intercepts, you know that those are the only possible places where you might cross, you might touch. You might touch, you might cross. You don't know which necessarily. But anyway, we know it's going to go up. Now I want to figure out what's it going to do over in this region. So let's plug in one more value of x. How about just a half? So anyway, we've got y equals 2 there. If I plug in a half, let's come back up here. Let's erase this stuff. And let's start plugging in a half. I'd have 2 times a half. A half minus 3 is a negative 2.5. Okay. A half minus a 2 is a negative 1.5. And a half plus a 1 is a 1.5. And the key idea here is that this is positive something, right? You can solve for the point if you want, but it's positive something. So that tells me, well, I suppose I will solve for it. This would be a, let's see, that'd be like, oh, negative 2.5 over negative 2. It's going to be like a, well, I'm plugging in, man. I'm plugging in. It's like a 1.111. So, okay. So when x is negative hat, we're here at negative 1.11. Now again, it can't turn around and go down again because that would require an x-intercept. So it must be coming up there and climbing. And it must kind of somehow turn around and kind of go something like that. So it's climbing along the asymptotes there and there. Now you got to admit, that was kind of fun, right? Should put this next to the crossword puzzles in the paper. Maybe next to the Sudoku or something, you know? It's like, hey, graph a rational function. This will take you a little while. It'll be fun. It'll be enjoyable. But there, we've captured all of the essential behavior. So we got this asymptote. We got this asymptote. We know that it must sort of glom onto these things. We got this asymptote. We got this asymptote. We had this intercept. And we have these 2 points. That's enough to say, oh, it must be going up like that. And now here, we had this asymptote. We had this asymptote. We had this point. We did plug in this point to make sure it was going down. And there. Nifty. That's nifty. Well, kind of a lot happened there, right? And there's actually one more thing that's going to happen that I haven't shown you yet. So it's worth coming through another example. Now, you might want to pause for a second and ask yourself, okay, how would I approach this? Okay, I hope you only paused for 1 second, because how would you approach this? Well, the first thing to notice that's different here is it's yucky, right? But notice up here, this problem here, that wasn't quite as yucky. Why? Because it was all factored out for us, right? It was all nice and factored out. We need to, what's going on here? We need to factor this puppy is what we need to do. Factor first. So I'm going to do a lot of scribbly factoring work here, and then I'm going to erase it so that we can have room. But you're looking at the top, and you say, oh, that's one of those trinomial things you're supposed to try to unfoil. So x squared has to break up as x times x. It has to. There's nothing else. Please don't use negative x times negative x. That's, well, dorky, if I dare say it. Dorky. Okay, so anyway, we're going to use an x times an x. Now the 4 has to break up, well, it has to be either a 4 times a 1, maybe a negative 4 times a negative 1, or it could be a 2 times a 2, maybe a negative 2 times a negative 2, right? That's all the ways to break up the positive 4. And since my goal is to have my inner and outer products here add up to negative 4, I know this has to be the minus 2 and the minus 2 option. That way my outer product is a negative 2x and my inner product is a negative 2x, and those will add up to negative 4x. And by the way, a negative 2 times a negative 2 really is a positive 4. So that works. So it's x minus 2 times x minus 2. Now allow me to get rid of all that. Delete. So the top is going to be, let's try to remember this now. It was an x minus 2 times an x minus 2. I suppose I could say x minus 2 with a square on it, but I like to just kind of separate them out when I'm doing these kind of graphs. Now the bottom thing. Oh boy. So that's one of those 4-term puppies. So remember the factoring by grouping. First, you kind of look at the first 2 terms. You say, what can I pull out? I can pull out an x squared. What would that leave me? It would leave me with a 2x plus a 3. Then because it's a minus, I put a minus. And then I look at these 2 terms, and I say, what can I pull out? I can pull out a 4. And then here, you want to think of it as though you had just pulled out a negative 4. So you pull out a negative 4 from a negative 8, you get a 2x. You pull out a negative 4 from a negative 12, you get a plus 3. This is the part you have to be careful about, is that sign. It looks negative over here, but it's positive over here. And again, why? Because this says negative 8x minus 12. That's what this says, and that's really what we wanted. Okay, cool. Get out of the way. Get out of the way. Okay, so now we have to, we were hoping that this would happen. We've got a common factor in both of these 2 terms, right? Remember, it's this is what separates the thing into 2 terms. It's like, I'm multiplying, and then this gets grouped, so you count that as one object. This group times this, yep, minus. Ooh, change of pace there. And then this group times this is a multiplication. Okay, so we've got 2 terms, and both of those terms has a common factor of 2x plus 3. So you could, if you want, pull out the 2x. You could, if you want, use a pen. You could, if you want, pull out the 2x plus 3. Kind of think of undistributing the 2x plus 3 to the front, taking it out to the front. And then that'll leave you with the x squared here minus the 4 over there. Right? So it's like, yeah, it works. So actually look at this. We should always factor completely. That's a difference of 2 squares. So that's an x minus 2, x plus 2. So to finish this up, I'm going to put the x minus 2 and the x plus 2 first, and then I'm going to put the 2x plus 3 like this. So that's the result of all of our factoring. Now, I promised you there was something different here, right? There's something different here. You could call this, if you want to learn a cool sounding phrase, you could call this a removable singularity. What's a singularity? That's when you divide by 0. It's a problem, right? This one's, it looks like, oh my gosh, if I put x equals 2, I'm going to divide by 0. Except you're not, because look, it cancels. See? Huh? You're not really dividing by 0. So, no, or say, I should say not a vertical asymptote. That is not a vertical asymptote. So that's why I was saying it's before I was hesitating a little when I said, oh, whenever the denominator is 0, it's a vertical asymptote. I should say, well, almost. It's unless you can cancel it out. See, I can cancel out this x minus 2 here. So it's not a vertical asymptote. Point made? What is it? It's called a hole. It's a hole because you're still not allowed to plug in x equals 2. Because 0 over 0 is just as bad as dividing by 0. But it's not a pure division by 0. It's a 0 over 0. That's a different thing. We're going to have, in effect, a hole in our function right there. So what is our function then? Our function is this. The function that we're really trying to graph is this one. Do that cancellation. And note that there's a hole at x equals 2. Well, I'm not going to write it again. Just keep that in mind. There is a, at x equals 2, we have something called a hole. Okay. And I'll show you what that looks like on the graph when we get to it, which won't take long. Now, following our 5-step method, by the way, this is the simplified, this is what we're using to graph. We're looking at this when we make our graph. Okay, don't look at the original, that's a mess. And actually do the canceling too. Do the canceling and then look at what's left over, which is this. Here's the thing that we actually look at when we're making our graph. When we're doing things like, hey, what's the y-intercept? Well, you plug in x equals 0. Sometimes I go like this. Well, I guess I won't. You plug in x equals 0, so f of 0 is what now? Well, on top you'd have 0 minus 2 is a negative 2. On the bottom you'd have 0 plus 2 is a positive 2 times a, that would be a 0 plus 3 is a positive 3. So this is a negative 2 over 6, which reduces to negative 1/3. So we have a y-intercept at negative 1/3. One step down, not too many to go. I might as well graph that while I'm here. So there's a y-intercept right about there. Step 2, solve for any x-intercepts. And remember how you do that. X-intercepts, you look at the top here. You set the top equal to 0. When is the top equal to 0? X minus 2 equals 0 when x equals 2. And so that means we have an x-intercept at x equals 2. That would be over here. Okay, well, we got these 2 points. That's a good start. We got some points, man. Let's come over here and say, where are there vertical asymptotes or holes? The vertical asymptotes, like I say, we're looking at this one. We're looking at the denominator of the simplified, the reduced function. We look for look at 0 denominator. We say, well, there's vertical asymptote along. If you plugged in x equals negative 2, you'd have a problem. So along x equals negative 2. And also if you plugged in a, what would that be? Set 2x plus 3 equals to 0, you will get a negative 3/2. Right? Right. So we got 2 vertical asymptotes, and then we have a hole at x equals 2. So that's repeating this information from up here. So this is basically the the full answer to part 3. Does it have any vertical asymptotes or holes? Yeah, it has 2 vertical asymptotes and a hole. So x equals minus 2. Let's put that vertical asymptote in there. Let's put my glasses back on because they're falling off. Okay, so at x equals negative 2, we got a vertical asymptote. And remember, you always expect it to blow up. You expect, let's get some of this stuff out of the way. Let's get some of this stuff out of the way. It's going to get in our way. We don't want that. Okay, so you expect that it's either going to climb here or sink here. And on the left side, it's either going to climb here or sink here, right? That's the only 4 possible things that could, it's the only 4 possible things that could happen there. There's another vertical asymptote. Let's not forget that. At negative 3/2, are you kidding me? Oh, that's grody. Because that's like negative 1.5, right? No, this is gross. So we've got these 2 vertical asymptotes right next to each other. That's a bummer. Just because the graph is going to be such a bit of a pain there. So we got these 2 vertical asymptotes. Got the x-intercepts, got the y-intercepts, vertical asymptote. Okay, yeah. Now, in order to figure out the step 4, the horizontal asymptotes, are there any horizontal asymptotes? What you do is you think in terms of f of infinity. And so I'm looking at my simplified function again, and I've got an infinity minus 2 all over an infinity plus 2 times 2 times infinity plus 3. Okay, so the top, subtracting 2 doesn't change infinity. On the bottom, adding 2 doesn't change infinity. Now actually here, you don't want to ignore multiplication, so that's like 2 times infinity. But the plus 3 doesn't matter. Now the thing is, you've got basically infinity over 2 infinity squared. If you cancel some infinities, that's like a 1 over 2 infinity, which goes to 0, right? Because as you use a bigger number in your denominator, you go to 0. So there is a horizontal asymptote. It's along 0. It's along y equals 0. So let's see. Horizontal asymptote along y equals 0. As you use bigger and bigger values for x, you're going to expect to level out at y equals 0. So that's basically the boink, boink, boink. That is the x-axis here. So I'm going to draw my asymptote. So once again, notice you can cross a horizontal asymptote. It's just that you won't as you go towards infinities. It's not a cross touching. It's a leveling out. It's a approaching without touching. Okay, now's the part where we start to think about wet spaghettis, and we start to think about, like, let's look way over to the left here. It's pretty much either got to do this or this, right? Because there are no x-intercepts. It can't cross the x-axis over there because there are no x-intercepts over there. So it has to be one of those 2 behaviors. How do you choose between the 2? You just have to plug in 1 point. 1 point will tell you whether you're positive or negative. So let me plug in, let me come over here. Let me go somewhere. I'm going to shrink some stuff down. I love to do that because it makes, well, let's not do that. Okay. Let's shrink all of this stuff down. Why does it let go? Shrink down. Shrink it good. Okay. And then let's take all of this stuff over here and shrink it down. In fact, I'm going to shrink it and move it over here. Woo! You gotta love tablets, man. You gotta love them. So anyway, what I was trying to figure out is what's going on, like, over here, right, on the left side. So I need to plug in a value of x that's on the left side. So here I go, I'm plugging in some x's over there. Maybe I'll just plug in, I don't know, -4. So looking at my function, I'd have a -4 minus 2 is a -6 on the top. -4 plus 2 is a -2. Let's see, 2 times -4 is -8, plus 3 is a -5. Okay, notice this is a negative, it's 6/10. So when x is negative 4, 1, 2, 3, 4, I'm at just about here. Okay, that's enough. That's all I need to know, because I'm only interested in the general behavior here. You know it levels out at that asymptote. You know it can't cross the x-axis over here. It must sink along this asymptote. Good. It's a wet spaghetti thing. Good. Good. We nailed it. Let's come over here. We know it has to go through these 2 points. Question. When I'm over here, is it sinking or is it going down here or is it going up here? Well, plugging in a value of x will tell you. And it looks like a good value of x to plug in might be negative 1. Let's just see where we are. So again, looking at my function. Negative 1 minus 2 is a negative 3 on the top. Negative 1 plus 2 is a 1 on the bottom. 2 times negative 1 is negative 2 plus 3 is a 1 on the bottom. Oh, I'm at negative 3. How do you like that? So when x is at negative 1, I'm down here. Well, that nails this. It must be doing something like this. And it has to come towards this. Now, here, I'm not quite sure. It could do one of 2 things. It could either cross the x-axis and then sort of come back down, or it might just bounce off the x-axis and kind of come down this way. Which is it? I don't know. Just plug in a value of x and find out. How about if we plug in x equals, I don't know, positive 4? How's that sound? So plugging in positive 4 to this function again. On the top, 4 minus 2 is a 2. On the bottom, 4 plus 2 is a 6. 2 times 4 is 8 plus 3 is 11. This is 2 over 66. It's small, but the point is it's positive. So how do you like that? It really did. It crosses over into positive territory here. But you know it has to level out, so it's not going any higher. It has to level out along that asymptote. Boinkity boink boink boink. And I suppose I could, really you should remember this. You should always, you should always, let's put a PS here. Come off it. Jeepers creepers. Okay, so anyway, PS. Always show any asymptotes, holes, arrowheads, etc. And while I'm mentioning holes, remember we have a hole here? We were saying before that we have a hole at x equals 2. Well, where is it? Well, it turns out this does not really count as an x-intercept. I have to erase that. This is how you do a hole. Oh, this is going to be hard because it's going to take everything off, isn't it? Ugh. Okay, good. This is a hole, not an x-intercept, but a hole. And you draw the hole as a big empty circle. So wherever the graph was, where you thought it was going, just kind of erase a little spot and make a little hole. Okay, this is a hole. Okay, that's how you handle your holes. So at first what you do is you say, oh, there's a hole. I'll worry about that later. Then you make a graph, and then at some point you say, oh, I have to erase that point and put a hole. Okay. Turns out it was right there where we thought we had an x-intercept. So you know what I have to do also is I have to come back here to say, that's not an x-intercept. It's a hole. You can't say it touches the x-axis if it's a hole. So, got to be careful with this stuff. So be wary of your holes. Now, lest you think we're done, we still don't know what's going on in between the 2 asymptotes. So this is why I was going, sheesh, those asymptotes are awfully close. We're going to have to plug in something here. Let's get the green here. How about if I plug in, let's see, that's between negative 1.5 and 2, huh? How about if I plug in a negative 1.75 in it? Let's see if we're either up above the axis somewhere. I mean, we're either up here doing something like this, or we're down here doing something like this. Again, there's no x-intercepts there, so we're not crossing. We have to glom on to both asymptotes. So it's either this U-nail up here, or it's this kind of a U-nail down here. Which is it? Well, you just plug in another value of x to find out. So what am I plugging in? Negative 1.75? Yep, that's what I'm trying to do. Negative 1.75. What do we get? Well, looking again at our function. Negative 1.75 minus 2 would be a negative 3.75 on the bottom. Negative 1.75 plus 2 would be a positive 0.25. And then here, A negative 1.75 times 2 is a negative 3.5, and a negative 3.5 plus 3 is a negative 0.5. Now the number is almost not interesting to me, but I might as well get it. 3.25 divided by... if you want to not get Alzheimer's, you should try to do these things in your head always. But I'm getting 26. It's way the heck up there. But the most important part is that it's positive, which means we are definitely above. So I'm just going to kind of go like this. Whoa. It's up there. Way up around y equals 26. You have this U-nail type thing. Make sure you remember to capture behavior in between all the asymptotes. I got an asymptote. Well, what's it doing over here? What's it doing in between? What's it doing over here? So it's always 3 questions when you have 2 vertical asymptotes. So if you have more vertical asymptotes, make sure you capture the behavior in between every pair of asymptotes. That was a cool example. Oh my gosh, I was having fun. I hope you were having fun. You got to admit, it's like, well, it's fun. Can you imagine trying to graph this just by making up values of x and going? You know how insane you would go? Because you'd be saying, oh, it seems to be here. Oh man, it's sinking. Oh, yeah. What the heck? I'm up here now. Oh my, I'm back down here now. Ah. You know what I mean? It's not a fun experience if you're doing XY tables. But if you have a little wisdom, a little graphing wisdom, asymptotes, intercepts, and the idea that it's a wet noodle graph, then these things are actually funner than a Sudoku, if you ask me. All right, can I find the off button with one eye?